full chapter of solid state in one shot. In this lecture, I will teach you the full chapter of solid state in a very short period of time. I will use my personal tricks and techniques which you will not find anywhere. So watch this lecture till the end and you will enjoy learning this difficult chapter in the most easy way. Firstly, let me teach you the basic concept of solids. We all know that solids have definite shape and definite volume. Secondly, there is strong intermolecular forces present between the particles of solid. Thirdly, solids cannot be compressed and they do not fill the container like gases. These are the basic properties of all solids. Now let me teach you the types of solids. There are two types of solids: crystalline solids and amorphous solids. In crystalline solids, all the particles are arranged in a regular way. For example, these particles are regularly arranged in a three-dimensional pattern in the space. In amorphous solids, particles are arranged in irregular way. For example, these particles have irregular arrangement in the space. Secondly, in crystalline solids, there is long order and arrangement of particles. For example, these particles have long order of arrangement. In amorphous solids, there is a short order and arrangement of particles. For example, these particles are regularly arranged and these particles are irregularly arranged. Thirdly, crystalline solids are called true solids. They are therefore called true solids because they have true properties of solid. For example, they have regular arrangement, long order, etc. Personally, I say that they are perfect solids, while amorphous solids are called pseudo-solids or supercooled liquids. They are therefore called pseudo-solids because they have fake properties of solids. For example, they have no regular arrangement of particles, they have no long order of particles, etc. Personally, I say they are imperfect solids. On the other hand, they are also known as supercooled liquid because they have the ability to flow over time if temperature changes. Fourthly, crystalline solids have sharp melting points. The range of melting points of crystalline solid is less than 5 degrees centigrade. For example, the melting point of sodium chloride is 801 degrees centigrade. It may increase or decrease by 5 degrees centigrade depending upon several factors. On the other hand, amorphous solids have ranged melting points. The range of melting points of amorphous solid is greater than 5 degrees centigrade. For example, the melting point of a glass is from 1400 degrees centigrade to 1600 degrees centigrade. Fifthly, crystalline solids are anisotropic in nature, while amorphous solids are isotropic in nature. For example, anisotropic properties means crystalline solids have different physical properties in different directions. For instance, consider wood. The speed of light would be different in different direction. On the other hand, amorphous solids have same physical properties in different directions. For instance, consider this glass. The speed of light would be the same in all directions of glass. Lastly, the examples of crystalline solids are salt, iron, gold, sugar, etc. While the examples of amorphous solids are glass, rubber, wax, etc. Thus note down all these important points about crystalline solids and amorphous solids. Here, let me teach you one important question. Why is glass called a supercooled liquid? Well, we already know that glass is an amorphous solid. Secondly, all the molecules in the glass are irregularly arranged. Due to this, molecules of a glass can flow if temperature changes. So remember that if we increase the temperature of a glass, it can flow like a honey. That's why we call it supercooled liquid. Hence note down this important question. Now let me teach you the four types of crystalline solids. like ionic solids, metallic solids, covalent solids, and molecular solids. To learn all these 4 types of crystalline solids, I teach my personal trick. I say ionic solids contain ionic bond, metallic solids contain metallic bond, covalent solids contain covalent bond, and molecular solids contain covalent bond. Now we can easily understand each type of solids on the basis of their respective chemical bond. For example, ionic bond is present in sodium chloride, magnesium oxide, calcium carbonate, etc. Metallic bond is present in metals like iron, gold, silver, copper, etc. Covalent bond is present in non-metals like diamond, graphite, etc. Covalent bond is also present in molecular solids like ice, sugar, etc. Now I just tried the physical properties of these compounds. We know that ionic compounds like sodium chloride are made up of cations and anions. For example, sodium is a cation and chlorine is an anion. Secondly, ionic solids have high melting points. Thirdly, they are brittle. It means that they are hard but break easily. Fourthly, they are good insulators in solid state. It is because they have no free ions in solid state. Fifthly, they are good conductor in molten or liquid state. It is because they have free ions in molten or liquid state. On the other hand, we know that metallic solids like iron are made up of only iron atoms. Secondly, according to electron C theory, they have C of delocalized electrons. Thirdly, they have high melting point. Fourthly, they are malleable and ductile. Remember that the word ductile means we can make thin wires from metallic solids, and the word malleable means we can hammer or press metallic solids without breaking. Fifthly, they are good conductor of electricity. It is because they have C of delocalized electrons which freely move inside the lattice. On the other hand, we know that covalent solids are made up of nonmetals like carbon atoms. Secondly, they have high melting points. Thirdly, they are hard in nature like the pencil we use. Fourthly, they are poor conductor or semiconductor of electricity. For example, diamond is a poor conductor of electricity, while graphite is a semiconductor of electricity. Lastly, molecular solids are made up of molecules like sugar. Secondly, they have low melting points. Thirdly, they are soft in nature. Fourthly, they are insulator or bit conductor of electricity. It is because they have no free ions or no free electrons. Thus noted down these 4 types of crystalline solids. Now let me teach you the basic concept of crystal lattice and unit cell. We all know that every solid is made up of constituent particles. Constituent particles may be either atoms, ions, or molecules. Now here is one important question. How these constituent particles combine together to form big structures of solid? Well, to learn this question, let me give you one simple example. We know that when many bricks combine together, they form a room. When many rooms combine together, they form a building. Similarly, when many lattice points combine together, they form a unit cell. When many unit cells combine together, they form a crystal lattice. So lattice point is like a brick, unit cell is like a room, and crystal lattice is like a big building which contains many unit cells. Now consider this 3D structure of a sodium chloride. Here, let me ask you, can you spot lattice points, unit cell in this crystal lattice? Well, this dot is one brick or one lattice point. This cube is one unit cell. This whole thing is a crystal lattice. Thus we define lattice point as, in crystal lattice, each atom, ion or molecule is represented by a single point, dot, is known as lattice point. Secondly, We define unit cell as the smallest repeating part of a crystal lattice is called unit cell. Thirdly, we define crystal lattice as the regular arrangement of the atoms, ions or molecules in a 3D space is called crystal lattice. Thus remember that lattice point is a smallest unit like a brick, unit cell is like a room, and crystal lattice is like a big building. Now let me teach you the types of unit cell. Mainly, there are two types of unit cell, primitive unit cell and non-primitive unit cell. In primitive cell, particles are present only at corners. For example, consider SCC or simple cubic cell. In this unit cell, we can see that all particles are present only at different corners. In non-primitive cell, particles are present at corner as well as at other position. Remember that non-primitive cell is further divided into three types like BCC, FCC and ECC. BCC stands for body-centered cubic cell, FCC stands for face cubic cell, and ECC stands for edge-centered cubic cell. Now in these three types of unit cell, particles are present at corners. So I write particles are present at corners, particles are present at corners, particles are present at corners. Now there is a word body-centered. So particles are also present at body center. For example, consider this unit cell. Here, particles are present at corners as well as at body center. Secondly, there is a word face-centered. So particles are also present at face center. For example, consider this unit cell. Here, particles are present at corners as well as at face center. Thirdly, there is a word edge-centered. So particles are present at edge center. For example, consider this unit cell. Here, particles are present at corners as well as at edge center. Thus note down all these important types of unit cell. Now let me teach you different parts of a unit cell which is often ignored. Consider this unit cell. This is the corner of a unit cell. Secondly, this is the edge of a unit cell. If I ask you where is the edge center, you can easily spot this position. Thirdly, this is the face of a unit cell, and I hope you can spot this point as a face center. Lastly, this is the body center. Thus note down these different parts of a unit cell. Now I will teach you the most difficult concept of this chapter in the most easy way. I usually ask this difficult question. What is meant by contribution of an atom in a unit cell? Believe me, 90% student cannot answer this question. To learn this concept, I will teach you two examples by two different methods. Consider this ball submerged in water. We can see that 50% part of this ball is above the water and 50% part of this ball is below the water. Now I cut the part of this ball above the water. Here, if I ask you how much part of the ball is present inside the water, your answer is simple, 1/2. We can say that the contribution of ball in the water is 1/2. Let me repeat it. We can say that the contribution of ball in the water is 1/2. Secondly, let's consider my friends. We collected $8 mutually and I put only $1 in this $8. So my contribution is 1/8 in this $8. Let me repeat it. My contribution is 1/8 in this $8. Similarly, consider this unit cell. Let this atom is present at corner. Now this atom seems to be present completely at corner, but according to experiments, we have observed that only 1/8 part of this atom is present inside the unit cell. Let me repeat it. only 1/8th part of this atom is present inside the unit cell. This contribution of an atom inside a unit cell means that how much part of an atom is present inside the unit cell. So note it down, this very important point. Now let me teach you my personal trick of contribution of an atom inside a unit cell. I challenge you that you will not find this trick anywhere. Consider this unit cell. I write BC, I skip D, and I write EF. This B stands for body-centered, this C stands for corner, this E stands for edge-centered, this F stands for face-centered. Now listen carefully. I write 18. I subtract 6 from 18, I get 12. Then I subtract 6 from 12, I get 6. Now this one means there is only one body centered in a unit cell. This 8 means there are 8 corners present in a unit cell. This 12 means there are 12 edges in a unit cell. This 6 means there are 6 faces present in a unit cell. Secondly, I write 1, 1, 1. Now I write this one as it is in the denominator. I also write this 8 as it is in the denominator. Now I divide 12 and 6 by 3. I get 4 and 2 and I write them in the denominator. Remember that these numbers shows the contribution of atoms in a unit cell. For example, if an atom is present at body centered, its contribution is 1. If an atom is present at corners, its contribution is 1/8. If an atom is present at edge center, its contribution is 1/4. If an atom is present at face center, its contribution is 1/2. Thus note down this trick of contribution of atoms. Now I will show you the power of this trick. For example, calculate the number of atoms present in a unit cell. Well, I write BCEF. I write 18. I decrease it by 6 successively. I write 12 and 6. I write 1, 1, 1. I write 1, 8. I divide 12 and 6 by 3. I get 4 and 2. We already know that there are 4 types of unit cells like SCC, BCC, FCC and ECC. SCC stands for simple cubic cell. Remember that it is also known as primitive unit cell. For example, its structure is like this. Atoms are only present at corners. Now the total number of atoms is equal to, we can see that there are 8 corners. Secondly, the contribution of each atom and the corner is 1/8. So 8 into 1/8 equals 1 atom. Now here is one important question which I often ask. What is this 1 atom means? Well, it means that 8 atoms on 8 corners of this unit cell show only 1/8 part each. Overall, we get only 1 atom. Thus in this unit cell, overall, there is only 1 atom present. Secondly, BCC stands for body-centered cubic cell. For example, its structure is like this. We know that in body-centered cubic cell, particles are present at corners and at body center. So I will find the number of atoms at corner and at the body center. Number of atoms is equal to, there are 8 corners and the contribution of each atom is 1/8. So 8 into 1/8 equals 1 atom. Also, number of atoms is equal to, there is only one body center and the contribution of an atom is 1 at the body center. 1 into 1 equals 1. Now the total number of atoms is equal to, 1 plus 1 is equal to 2 atoms. Thus overall, we get only 2 atoms in body-centered cubic cell. Thirdly, FCC stands for face-centered cubic cell. For example, its structure is like this. We know that in face-centered cubic cell, particles are present at corners and at face-centered. So I will find the number of atoms at the corner and at the face center. Number of atoms is equal to, there are 8 corners and the contribution of atoms at corner is 1 by 8. So 8 into 1 by 8 equals 1. Also, number of atoms is equal to, there are 6 faces and the contribution of an atom at faces is 1 by 2. So 6 into 1 by 2 is equal to 3. Now total number of atoms is equal to 1 plus 3 equals 4 atoms. So there are total 4 atoms present in face-centered cubic cell. Fourthly, ECC stands for edge-centered cubic cell. For example, its structure is like this. We know that in edge-centered cubic cell, particles are present at corners and at edge center. So I will find the number of atoms at the corners and edge center. Number of atoms is equal to, there are 8 corners and to 1 by 8 equals 1 atom. Also, number of atoms equal to, there are 12 edge center and to the contribution of each atom at edge is 1 by 4. So 12 into 1 by 4 equals 3 atoms. Now total number of atoms is equal to 1 plus 3 equals 4 atoms. Thus overall, there are 4 atoms present in edge-centered cubic cell. Hence using this trick, we can easily calculate the number of atoms in a unit cell. Now let me teach you that using this trick, we can easily calculate the formula of any unit cell. For example, A atoms are present at corners, B atoms are present at edge-centered, and C atoms are present at face-centered. Find the formula of a unit cell. Well, we know that A atoms are present at corners, so number of A atoms is equal to, there are 8 corners in a cubic cell and the contribution of each atom at corner is 1 by 8. I get 1 atom. Secondly, B atoms are present at edge centered, so number of B atoms is equal to, there are 12 edges in a cubic cell and the contribution of each atom at edge is 1 by 4. I get 3 atoms. Thirdly, C atoms are present at face center, so number of C atoms is equal to, there are 6 faces in a cubic cell and the contribution of each atom is 1 by 2. I get 3 atoms. Thus there is 1 atom of A, there are 3 atoms of B, and there are 3 atoms of C. The formula of this unit cell is AB3C3. Hence using this simple trick, we can easily calculate the formula of any unit cell. Now let me teach you the 6 parameters of a unit cell. For example, consider this unit cell. Remember that every unit cell is described by 6 parameters, 3 sides and 3 angles. Now as a convention in chemistry, the edge length of x-axis is represented by A, the edge length of y-axis is represented by B, and the edge length of z-axis is represented by C. On the other hand, the angle opposite to the A edge is known as alpha, the angle opposite to the B edge is known as beta, and the angle opposite to the C edge is known as gamma. These angles are also known as interfacial angles. So remember that a unit cell is described by 6 parameters, 3 edge lengths, ABC, and 3 facial angles, alpha, beta, and gamma. Now it is time to teach you the most easy trick of 7 crystal system, which you will not forget in your entire life. I hope that you must have watched Tom and Jerry in your life. I always say, see Tom there. C stands for cubic, T stands for tetragonal, O stands for octahedral, M stands for monoclinic, T stands for triclinic, H stands for hexagonal, and R stands for rhombohedral. Now what about edge length and interfacial angles? Well, the first and the last have the same edge length. A equals B, B equals C. Also, A equals B, B equals C. the second and the second last have the same edge length. A equals B, but B doesn't equal C. A equals B, but B doesn't equal C. These three remaining have the same edge length. A is not equal to B, B is not equal to C. A is not equal to B, B is not equal to C. A is not equal to B, B is not equal to C. In case of interfacial angles, the first three angles are equal. Alpha is equal to beta, beta is equal to gamma, gamma is equal to 90 degree. Also, alpha is equal to beta, beta is equal to gamma, gamma is equal to 90 degree. Alpha is equal to beta, beta is equal to gamma, gamma is equal to 90 degree. Now there is a letter M and a monoclinic. If I rotate this M 90 degree clockwise, it is like B or beta. I write beta here. It means alpha is equal to gamma, gamma is equal to 90 degree. Secondly, there is a word tri and triclinic. It reminds me that three angles are not equal. I write alpha is not equal to beta, beta is not equal to gamma. Lastly, I write alpha is equal to beta, beta is equal to 90 degree, alpha is equal to beta, beta is equal to 90 degree. Here gamma is 120 degree and there gamma is not equal to 90 degree. Thus using this simple trick, we can easily learn 7 crystal system in a very short period of time. Hence noted down this super easy trick. Now let me teach you closed packing in crystal system. To learn this concept easily, we must learn coordination number. Coordination number is equal to total number of touching spheres. For example, consider these constituent particles. Remember that in case of close packing, I will not use the term constituent particles. Rather, I will use the word sphere because particles look like sphere in close packing. Now here, if I ask you how many spheres are attached to A, your answer is 1. So the coordination number of A equals 1. Secondly, B is attached to 4 other spheres. So the coordination sphere of B is 4. Thus coordination number is the total number of touching spheres. Now what is closed packing? Well, closed packing means occupying maximum space and there is minimum empty space. For example, consider these spheres. Now in first case, there is maximum space occupied by the 4 spheres and there is minimum empty space. So it is a closed packing and its efficiency is high. In the second case, there is minimum space occupied and maximum space is empty. So it is not a closed packing and its efficiency is minimum. Remember that there are 3 types of closed packing like 1D closed packing. Now if the coordination number is 2, usually it is known as 1D packing. For example, consider this case. Here we ignore the corner spheres. This sphere is attached to 2 other spheres, so its coordination number is equal to 2, hence it is 1D close packing. Secondly, 2D close packing. It is further divided into 2 types, SCP, HCP. SCP stands for square close packing and HCP stands for hexagonal close packing. We know that in square there are 4 sides. Thus if coordination number is 4, it is known as SCP or square close packing. For example, consider this closed packing system. Let I select this sphere. We can see that it is attached to 4 other spheres. The coordination number is 4. Hence it is SCP or square close packing. Remember that these 2 layers are same. We call this layer as A layer and we also call this layer as A layer. So it is also known as AA type arrangement. On the other hand, we know that there are 6 sides in any hexagonal shape. Thus if coordination number is 6, it is usually known as HCP or hexagonal close packing. For example, consider this closed system. Let I select this sphere. We can see that it is attached to 6 other spheres. Its coordination number is 6. So it is HCP or hexagonal close packing. Remember that this layer is different from this layer because the atom of this layer is not touching the atom of first layer. So this is A layer, this is B layer, and this is again A layer. Thus it is also known as ABA type arrangement. Here, let me teach you one bonus MCQs. Which closed systems has more efficiency, SCP or HCP? The answer is HCP because there is minimum empty spaces in it, while SCP has less efficiency because there is more empty spaces in it. Thirdly, 3D closed packing, which a lot of students do not understand easily. To learn 3D closed packing, let me teach you my personal trick. Consider these 2 layers. We know that this layer is just above the second layer. They both are the same layers. I call this layer as A layer and I also call this layer as A layer. On the other hand, consider these 2 layers. This is A layer and this is slightly towards right, so it is B layer. Now there are 2 types of 3D close packing, CCP and HCP. This CCP stands for cubic close packing. We know that in 3-dimensional close packing, we need 3 layers. So I select 3 layers, A layer, A layer and A layer. I write 151. This 1 means I take 1 sphere in first layer. This 5 means I take 5 sphere in second layer. And this 1 means I take 1 sphere in third layer. Now this is top layer, this is middle layer and this is bottom layer. This sphere is attached to 4 other spheres of its own layer, while this sphere is also attached to 1 sphere of top layer and 1 sphere of bottom layer. So its coordination number is 6. We can see that there are 3 A layers. We call this as AAA arrangements. Secondly, HCP stands for hexagonal closed packing. We already know that in 3-dimensional packing, we need 3 layers. In case of hexagonal closed packing, I select A layer, B layer and A layer. I write 373. This 3 means I take 3 spheres in the first layer, 7 spheres in the second layer and 3 spheres in the third layer. Here, this is top layer, middle layer and bottom layer. Now this sphere is bonded to 6 other spheres of its own layer. Also, it is attached to 3 spheres of the top layer and it is attached to 3 spheres of the bottom layer. So its coordination number is 12. We can see that there are AB layers, so we call this as AB arrangement. Thus noted down this 3D close packing, which a lot of students are not understanding. Finally, let me teach you types of voids in closed 3D packing. Well, voids are empty spaces present between spheres. There are 2 main types of voids like tetrahedral void and octahedral void. The word tetra stands for 4 spheres and the word octa stands for 6 spheres. Now void formed among 4 spheres is called tetrahedral void. For example, consider this. Here, these 3 spheres are present in bottom layer while this 1 sphere is present in top layer. Now the empty space or void among these 4 spheres is called tetrahedral void. Secondly, the void formed among 6 spheres is called octahedral void. For example, here these 3 spheres are present in bottom layer and these 3 spheres are present in top layer. Now this void among these 6 spheres is called octahedral voids. So remember that tetrahedral void is formed among 4 spheres and octahedral void is formed among 6 spheres. Now here is one important question. How can we find tetrahedral and octahedral voids and different unit cells? Well, I write SCC, BCC, FCC and ECC are simple cubic cell, body-centered cubic cell, face-centered cubic cell and edge-centered cubic cell. I write 1 atom, 2 atoms, 4 atoms, 4 atoms. Now N stands for number of atoms in a unit cell. Remember that octahedral voids in any unit cell is equal to N or number of atoms present in a unit cell. Secondly, tetrahedral voids in any unit cell is equal to 2N. For example, in FCC, there are 4 atoms. So it has 4 octahedral voids and 8 tetrahedral voids. Similarly, in BCC, there are 2 atoms. So it has 2 octahedral voids and 4 tetrahedral voids. Thus, using this trick, we can easily calculate tetrahedral voids and octahedral voids in any unit cell. Lastly, let me teach you density of a unit cell. Firstly, I write SCC, BCC, FCC, ECC are simple cubic cell, body-centered cubic cell, face-centered cubic cell, edge-centered cubic cell. Now I write 1 atom, 2 atoms, 4 atoms and 4 atoms. We already know that density is equal to mass upon volume. Here, density is equal to Z(n)(m) upon A cube Na. This Z is the number of atoms in a unit cell, M is the molar mass, 8 is the volume of a unit cell, Na is the Avogadro constant, which is 6 into 10 to the power 23. Now consider this question. Silver crystallizes into FCC structure. The edge length of a unit cell is 408.7 pm. Calculate the density of a silver if the molar mass of a silver is 108. Now according to the given data, A equals 408.7 pm. Remember that I always convert pm into centimeter. So I write 408.7 into 10 to the power negative 10 centimeter. Secondly, the molar mass of a silver is 108. Thirdly, we can see that in FCC there are 4 atoms present. So Z represents the number of atoms which is equal to 4. Na is the Avogadro constant which is 6 into 10 to the power 23. Now I can easily solve this question. I write density is equal to Zm upon A3Na. I plug in all these values in this equation. After calculation, I get 10.51 gram per cm cube. Remember these two very important points, which is the common mistake of a lot of students. I will always convert the length of edge from picometer to picocentimeter. Secondly, the unit of density is gram per cm cube in chemistry, while in physics, it is kg per meter cube. So remember these two important points whenever you calculate density numericals in chemistry. I hope that you have learned this chapter of solid state in a very easy way.